So homework 7, page 131. Still in section 3.2. Now this time we're doing 1 through 11 odd. 33, 35, 39, 41, 43, 53. So, okay. This is what this is like the whole point. This is like the first half of calculus right here. Is this idea, right? That the derivative of a function is this. We set up the difference quotient, right? There's the rise over the run if it's set up this way. But I did want to say there are a bunch of equivalent ways we could write this. Okay, so like for instance, what you could do is something like the limit as maybe y goes to x of f of y minus f of x over y minus x. And you can see how that works, right? Like if I replace, instead of an x plus h, if I replace this with a y, right? And that's all that's happening there. Now we have f of y. And we're just saying as y gets closer to x, that's what's going to happen. You could also have written this the other way around, just like with any slope, right? As y goes to x, as long as you do, as each point, right? Like any 2 points, right? Just think back to algebra 2, right? You have any 2 points. It doesn't matter how you set it up, right? As long as you're taking that point, let's say first, you go, you could go 2 minus 4 over 1 minus 3, and you get the same thing as if you did 4 minus 2 over 3 minus 1. You could
factor a negative out of something.
Exactly, right? So this is the same kind of thing here, right? As long as your points, you have your x's first, okay, so then put your x's first. Your y's second, put your y's second. Or put the y's first, it won't matter. It'll give you the same thing, right? Because we're just talking about setting up a slope here, right? And then taking the limit as that distance gets infinitely small. There's a little bit more creative way of doing this, which is instead of, this is the point you care about, instead of going over here to h and then setting that up that way, so now you're at x plus h, another way is to also go back by a distance of, say h. So you're at x minus h. And now you have another one here, f of x minus h. And now what you set up is the limit as h still, we're dropping h down to 0, but now it's f of x plus h minus f of x minus h. Now instead of it being over a distance of h, it's over a distance of 2 h's, right? Yeah. And you can see that in the limit, in all of these cases, no matter how you want to set this up, the idea is the same. We're letting this distance here get infinitely small, and by plugging that into the function, the distance here also gets infinitely small, but you're setting up, in every case, a rise over a run. Or, the way of thinking about it is, you're taking, what have you set up? Your rise over your run, the change in y over the change in x, and you're taking the limit as delta x goes to 0. Now, in this case, your delta x happened to be h, and so h is going to 0. Here, you can see that's your delta x. That's your change in x right there with your x and your y. I don't have y here anymore. But that's also, that is going to 0. The delta x is going to 0. So this kind of, in general, this is what you're doing. You're letting that go to 0. Of course, y, it being a function, also makes that go to 0. So they're both going to 0. But here's the thing. Check this out. Here's some notation for you. This delta y over delta x, once you take this limit, there's a nifty notation for this, and it's dy dx. And you could think about it as in the limit, these distances, right, your deltas get infinitely small, and that's what the d kind of represents. It's an infinitely small distance, and this is a ratio. And this is indeed one of the ways you could write a derivative. So now here we've been using f and stuff like that. So let's just, now we're going to go into this because there's 1,000 ways that stuff could show up. So can I get rid of all this right now? Okay. The idea is just There's a bunch of equivalent ways of setting up a derivative. Sometimes they'll help you, sometimes they won't. Actually, there's one more I wanted to write. This one, usually the first one with the x plus h, that's the one that if you're trying to actually calculate a derivative, that's going to be the most straightforward way. But there are other times when maybe you want to use something else. And let's say you want to find the derivative here at some number a. And so you could go a plus h and etc. blah, blah, blah. Maybe for some reason you want to call it x. And so what you do is you plug in your f of x, you plug in your f of a, and indeed, now you have your difference quotient. Your rise is f of x minus f of a over x minus a. And we take the limit as x goes to a. And again, right, there's delta x is x minus a. You're letting that go to 0. This guy's coming down, and so again, you have your delta y over your delta x with your delta x going to 0. So I just want to throw that up there because there's a lot of different ways you're going to see this. This actually, writing it this way will help us prove something in just a minute. And so I want you to see that there are different ways of doing that. But now we're just going into some notation, okay? So given some function, we write its derivative is f prime of x. That's one way of doing it. Okay, but often our functions don't show up like this, and you just saw y show up a bunch. Oftentimes, how often do you see this, right? Sometimes sometimes if we want to really be sure that we're talking about a function and not just some number y, we'll be like this just to be clear here. And if that's the case, then yes, just as you expect, the derivative would be y prime of x. But here, if you don't have your of x or whatever, still we just call it y prime. Okay? So it doesn't have to be in this form. Anytime you see a prime, it means take the derivative of that thing. That's what that is. Now this is also the exact same thing as saying dy dx. That means the same thing. These two things mean the same thing. This means the exact same thing as dy dx. This, or you might even see it like this, d dx y, or d dx of y, something like that. We'll come back to this in just a second. This is the same thing as df dx, or d dx f. There may or may not be parentheses there. Sometimes there'll be brackets, whatever. Sometimes, like, if your f itself has a bunch of parentheses in it, like if here's your f, or your y, let's do y here. There's your y, and let's say it's like 2x squared minus 3 plus 1 all over 5x. Well then, it might make sense to use parentheses when you're saying take the derivative of it. So you could do this, d dx, that would mean the derivative of that thing. But just to be clear, since there's parentheses, you might put parentheses. Or since there's already parentheses, you might put brackets, right? There's just a bunch of different ways of seeing this, okay? Now, okay, so let me get a few things up here. Another thing to notice is if this weren't a function of x, if this were, say, a function of t, then you could write its derivative as f prime of t. You could write it as just f prime if you don't want to, the same way that we do right here. You could write it as df d. Now it's not x, it's t. This notation is really nifty because it helps remind you what your variable is. And it has some other things. Later on this year, we'll see it's very useful for other things we want to do too. Okay, but another thing, okay, here's yet another thing. D itself, the capital letter D can be used kind of like this. This says take the derivative of y with respect to x, right here. This says take the derivative of y, right there. You could also see that as in brackets or parentheses or something like that. And I mean, we could go on and on. There's a bunch of different ways of doing this, right? So I do want to get a couple of these up here. You're going to see this a lot. Well, just a second here. So these are all equivalent. dx f of x or dx of f of x. So, like, for instance, like, why might I write it like that? This right here, dx of, say, maybe we don't have the function named somewhere, right? Like, we don't have it on our paper, f of x equals x squared, and we just want to say take the derivative of this thing right here. It'll show up like that. And if you guys remember from last time, we did this. We took the derivative of this. What did it come out to be?
2x.
Yeah, 2x. That's what it came out to be. Okay, so that right there, that symbol, in one way it means take the derivative of this thing right here, and we did that, and so it's that. And so we'll get to that in a second. Now, ditto, if all of these were t's, you would have d dt of f of t. Or maybe d dt of just f if you're not putting the things there, but it's understood that f is a function of t, etc. There may or may not be brackets here or parentheses. It's all the same thing. So for instance, d dt of t squared is equal to what?
2t.
2t, right. The variable doesn't matter. I could have done smiley faces, right? But that's the idea here. Same thing if all of these were replaced with a capital D, right? Like if I had big capital D of some function t squared, I would say, yeah, 2t. You're not going to see this very often. We're almost always going to use this or the prime notation, which we'll get into in just a second, or which we've already seen and we'll get more into. But check this out. This is something I do want to say. These things right here, d dt of something, or big capital D of something, these are called operators. And in particular, these in particular are the differential. These are the differential operators. An operator, now I'm gonna boil this down. I'm not telling you something, I'm leaving some stuff out because I don't want to have to explain a couple of terms. But right now, you could think about an operator as a function which takes a function as an input and gives you a function as an output. So this thing right here, d dx, it's a function. And it takes a function as an input. It takes x squared. And what does it give you out? Another function, right? And there's a bit more to it, but that's what an operator is. And we've seen something like this before. We've had the domain function. It's not an operator because it takes a function and gives you back a set, right? Something like that. Right. Now that's not this f. Oh, we don't have an f. Okay, good. So just it takes a function as an input but gives you back a set, so it's not an operator. But the derivative operator is, right? dx takes a function as an input and it gives you back a new function as an output. That thing is called an operator. Just a bit more general than that. There's some stuff I'm leaving out, but if you think about it that way, you are good to go. Okay? Everybody with me? Okay, now we're also going to use prime as an operator. Okay, so the same way that I've done all of this right here, I could have just said, okay, take f prime. And what does that mean? Whatever f is, take the derivative of it, right? And I kind of think of operators as instructions, right? It's like it tells you something to do with a function, and the thing you get back is a function. And it turns out to be f prime, right? So like for instance, I might have just said t squared prime. That means whatever's in here, take the derivative of it. And so there's 2t. Or if it were x squared prime, just means take the derivative of that thing. So everybody with me on that? Okay, as we start to do this, right, so and actually I did want to have this up on the board. In both cases, whenever you see this, or you see something like this, in both cases, this means take the derivative of this stuff. Whatever's in there, it means take the derivative of it. This is nice because what if your function had a bunch of variables in it? What if you had y squared over x plus root x over 2y? Yeah, well, what's my variable here? Well, x is. And so that's everything else you could pretend is constant. This will, don't worry, we'll get there. We'll totally get there. This though, if it's not ambiguous, you see, this is where if I say take the derivative of that, you might go, well, that's ambiguous. Is y the thing I care about? Is x the thing? What's my variable? If it's known what the variable is, well then you could just use prime and there's no question about it. Blah 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 blah. Okay, everybody with me? That's just the basic the stuff we needed to get into, just so you know. And as we do all this stuff, the further we go, we're going to be doing it so often that you'll get a feel for it. This is like, you don't need to memorize any of that stuff. It does need to be said. But as we do it in class, you'll get a feel for how it's used, and et cetera, et cetera. So now, let's get into the lecture. Definition! A function f, call it f, is differentiable at a, so a is a number. A function f is differentiable at a if f prime of a exists, or if f prime of a exists. And remember, f prime of a is a limit. It's a limit as h goes to 0, or you could set it up different ways, but usually plugging in an a plus h minus f of a all over h. Here we're thinking about it as being, instead of thinking about it as a function, we're saying, well, let's evaluate that function at that number a. We could have said differentiable at x, and you'd have an x, whatever, right? Everybody get that? So that's what we mean by f prime of a exists. This limit does indeed exist. There's more to this. It is differentiable on the open interval AB. Okay, so differentiable on the open interval, blah, 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 blah. Now, it doesn't need to be a finite interval, right? It could be, you could say, or say a to infinity, or negative infinity up to a, or on all real numbers, infinity. This is an open interval. I'm not going to explain why it can't be a closed interval. I'll leave you to puzzle that out. If you're interested, bring it up Tuesday and we could talk about it. Okay, it's differentiable on this open interval if it's differentiable at every point in the interval. So this is very much like continuity, right? Like we're saying something, remember continuous is like a function is continuous at a number if the limit there exists, and it's continuous on an interval if it's continuous at every point in the interval. Same thing here, right? It's differentiable at a number if that limit exists. And it's differentiable on an interval if it's differentiable at every point in the interval. Does that make sense?
Yeah.
Okay. And you could puzzle out why it has to be open. It would be interesting if you could figure that out. Okay, and we could talk about it some other time, but it doesn't really matter. This is just, in fact, we're probably never going to think about this again. But anyway, here we go. So, I was going to come up with my own example, but they do a really good job in the book with example number 5. And this is on page 127. Because I have a certain way that I bring this up. The example in the book goes into like very, very good detail about other stuff that I'm not even going to bring up here. Okay, so if you want more on this, check out read the rest of that example. But here we go. It gives you f of x is equal to the absolute value of x, and it asks where is f differentiable? Where is it differentiable? And so, let's draw absolute value of x. What does the absolute value of x look like?
It's like, it looks like x when it's positive, and it looks like negative x when it's negative.
Yeah, there you go, right? And that just comes from the fact that absolute value of x is equal to just plain old x when x is positive. And it's equal to negative x when x is negative. And so negative x over here, positive x over here. Okay. Okay? Okay. Now, how did I want to do this? Let's see. It's pretty clear that when you're over here, what's the slope of this guy over here?
1.
Okay, good, right? I'm glad we don't need to think about that too hard. It's pretty obvious that the slope is 1 here, right? It's just the function x over here. Over here, what's the slope?
Negative 1.
Negative 1. Okay, so let's think about this. Now, really, right, and let's just think about, because now we're not just talking about slopes and lines, because we want this to be general, right? We don't. This happens to be an example where the slope is the same everywhere. It's just a line. But you could see if you take any point right here and you draw the tangent line, it happens to be the same exact line that the function is. And so yeah, its slope over here everywhere is 1. Its slope, if you go to any point over here and you draw its tangent line, it happens to be the exact same line, and so its slope is negative 1. Okay. How can you draw a tangent line right here?
At the bottom, just be x equals.
Right? And so right now we're not thinking about the definition of, like taking a limit and all that stuff. Let's just think about this geometrically, right? Like, and I've said before, like that really all of this is we're just finding the slope at a point. And if I choose this point right here, well, that slope looks like 1. If I go here, that point, it looks like 1. Same thing over here. If I go to a point over here, that slope looks like negative 1. But here, is it 0? Is it there? I mean, a tangent line would touch. There's infinitely many places that a tangent line could touch and not touch the rest of the function. So it's kind of like right here, the very idea of a tangent line isn't really defined. If we call this a corner. If there's a corner on a graph, you can't really define a tangent line. So we could say, in one sense, just looking at it geometrically, that the derivative doesn't exist there because the very concept of a tangent line breaks down. But what does that look like with the definition, the definition of a limit? Okay, so indeed, we can't draw a tangent line there because that doesn't make sense. So it looks like the place that we're going to have a problem, because it looks like this exists over here. Like, for instance, let's say we're at a equals 1. F prime of 1 would be what? What is the slope right there? It's 1. F prime of, say, negative 3 would be negative 1, because we're over here. The slope up here would be negative 1. So the only real problem we're having is what is f prime of 0? What the heck is that?
Well, we have to plug it in.
Let's plug it in. So let's just find out. And we're going to see how, in this case, this fails to be differentiable. Because our geometric intuition tells us something's amiss here. You can't, like, define a tangent line there. So what's going on in the definition? So I'm going to say, okay, right, just like we had before, if it's f of a, I'm going to go f of a plus h, but now it's f of x, you would say x plus h. There's a 0, so I'm going to go 0 plus h minus f of 0 all over h. What is f of 0 plus h?
F of h.
It's just f of h. And what is f of h?
Oh, absolute value.
Absolute value of h.
Of h. Yeah. Oh, yeah.
Yeah, minus absolute value of 0 all over h. Okay, limit as h goes to 0. Absolute value of 0 is just 0. So this is the limit of the absolute value of h over h. Now, this is a limit. So if it's going to 0, it has to agree from both sides. Otherwise, the limit doesn't exist.
Yeah.
Right?
Yes.
Aha. And so this is what this means, right? If this limit exists, this limit does not exist, and we're going to see why. Because remember what we have to do now with absolute values. We have to break this into two things and see if it works. So we're going to approach from the left. We're going to approach 0 from the left. Then we're going to approach 0 from the right. So limit as h goes to 0 from the left of absolute value of h over h. What is the absolute value of a negative number?
Positive.
It's the positive. So I'm going to take it and make it negative, right?
Yeah.
So yeah, I hate that, but that's how you do it, right? That's the definition of the absolute value. If the number's negative, make it negative. So negative h over h, right? Just imagine you're down at negative 1. You plug in your negative 1. H itself is negative 1, so you make it negative. Negative 1 is positive 1. That's how you do it, right? And so this works out to be the limit as h goes to 0 from the left of negative 1, which is a constant, and so it's just negative 1. On the other hand, if we do this, I'm just going to rewrite this guy. Do it from the right, then what is the absolute value of h if h is positive?
H over h, which is 1.
Just plain old h over h, which is just positive 1.
They don't.
And so they don't agree, so this limit does not exist. Therefore, it's not differentiable there. That's how it shows up analytically. And there's a bunch of different ways a limit might not exist, right? Like you might have a, think about functions. If they're discontinuous, right? And the limit going one place, the limit going from the other way ain't gonna work. Another way is if it blows up, limit doesn't work there, right? There's a bunch of different ways. This is one of the ways that a derivative might not exist. So let's do this now. So now that we figured that out, so where is it differentiable?
Everywhere but 0.
Everywhere but 0. And so I'm going to write that as negative infinity up to 0, union that with 0 up to infinity. That is where f is differentiable. Yeah. And so now let's graph f prime of x. Okay.
So it's just a line. Because it's just 1.
Over here it's 1.
Yeah, and it's a line there, but then negative.
Okay, so you're saying
X with
whenever x is positive, the slope is always 1. Now,
Yeah.
what happens here?
It is a circle.
There's a circle because you can't get to 0, right? Right? And so then what happens over here? What's its slope over there?
Also 1. Well, negative 1.
It's a negative 1. And so that's what it looks like. Yeah. Interesting, huh? And so it's not defined here, right? Because the derivative doesn't exist there, right? It's not differentiable at 0. And graphically, you could think about that. So you can't draw a tangent line there. What is the slope at a corner? That doesn't make sense. We saw analytically, it means that the limit doesn't exist. And so we have to pull that out. And there's no way of reconciling these guys together, really. So that's one way that a function can fail to be differentiable at a point. Differentiable everywhere else. The derivatives, that's a perfectly good function. That's a perfectly good derivative. Its slope is 1. Cool. This is a perfectly good function down here, right? It says the slope is -1. It's always -1 over here. Okay, cool. But there at 0 we have a problem. Okay? And like, if you wanted to, you could write this. You could say that this derivative is indeed, it's 1 if x is strictly bigger than 0, and it's -1 if x is strictly less than 0. And notice it's not defined at 0. You can't say less than or equal to, because again, you have a hole that you cannot get rid of. Okay? Everybody got that? Questions on that? Is this making you think of anything? I'm not suggesting that it should. I'm just is this making you think, remember what I said? Yeah. Don't, do you? 'Cause you weren't doing your homework. Okay, no. Okay. So here we go. This is cool. Or rather, here's another question. This is not an example of anything here. Let f of x equal that. Is f continuous at 0?
What continuous means?
And what does continuous mean?
The limit
If the, okay, so the limit of what as what?
of x goes to a.
As x goes to,
0.
and in this case our a is 0. So good. You're thinking of the definition.
F of 0.
Of f
Equal.
of x
Equal.
equals f
Of
of
0.
0, right? That's a, if you imagine that's an a, and that's an a. That's what it means to be continuous at a. If you take its limit and it goes to where it goes. So first, let's figure this out. What is f of 0?
0.
It's the absolute value of 0, which is equal to 0. And now, well, let's take the limit as x goes to 0 of f of x and see. F of x is just the absolute value of x.
She'll plug
Should
in
be
a 0.
0.
It's just 0.
It is, because we just did this, right?
Yeah.
Because from the left hand side, it's going to 0, so its limit is 0 from the left. And from the right, it's going to 0, so its limit is good from the right. So it agrees on both sides, and so by definition, it is continuous at 0.
Yeah.
So,
So it can be continuous, but not different.
yeah. So, f is continuous at x equals 0, but not differentiable at x equals 0. So, this is, I want to have this in your head before we do the very next thing. Because the very next thing is really, really nifty theorem. Everybody got that?
Yeah.
You could be continuous somewhere, but not differentiable there. So one way you could be not differentiable is if you're not continuous. Like for instance, right, you have something doing this, and then you have some, there's your function. It's not continuous here at A, and you can't define a derivative there. Right? That's kind of obvious that you can't. And if you use the definition of derivative, we'd run into the same thing that we ran into with the absolute value. You're going from one direction here, you're going from another direction here, it doesn't match up. And so, right? So clearly if it's discontinuous, but you could be continuous and not differentiable. So can you be differentiable and not continuous? Just think about what I'm saying, right? If
Yeah.
A, then B, that doesn't necessarily mean if B, then A, right? So now we're asking, so does this work the other way too? Or which way does it work? Does it work at all? I don't know. It turns out, here's the theorem. How do I have this? If F is differentiable at A, then it's continuous at A.
Okay.
So it turns out differentiable implies continuous, but continuous does not imply differentiable, because we just saw that continuous does not give you always differentiable. It might be, but you can't guarantee it. But if something is differentiable somewhere, then you can guarantee that it's continuous. So in other words, differentiability is stronger than continuity.
Okay.
So, yeah. Yeah. Okay, so here we go. Here's a proof. Suppose F is differentiable. Suppose F, I'm just going to put diffable. Suppose that F is differentiable at some number A. Okay, then by definition, that means that F prime of A, which is the limit as x goes to A of, now this is where, now we could just say, okay, well that means A plus H minus F of A all over H, but this is one of those cases where it will be useful to rewrite this. Now if we were just given an F and we're told to calculate the derivative, this would probably be the easiest way of going about doing it. But now for this proof, you'll see it will be useful to rewrite this as, oh, you see, I did x, I went ahead and did it. There's no x in there. That should have been as h goes to 0. You guys didn't catch me. You're both getting demoted or depointed, I don't know. Right? So as h goes to 0, that's the definition that we've been using for derivative. Let h get small.
Yeah.
But I said there's another way we could do it. We could let x go to a. Of what? Well, how about f of x minus f of a? Does that do the same thing?
Yeah.
X minus a. You give me any function here. We go to an x, we have an a, and you set up the difference quotient, right? That right there would be your change in y. That right there would be your change in x, and you let the change in x go to 0. Right? That's what we're doing. Everybody with me on that?
Yeah.
Okay. So if f is differentiable at a, that means that this limit exists. Yeah? Okay, good. Now what do we have to show? We have to show that it's continuous at A. And so we have to show, I'm just going to go put this up here, must show that what? What does it mean to be continuous at A?
The limit
The
as
limit
x goes to A of
As
f of
x goes to A of f of x
equals f of A.
equals f of A. That's what we need to show. Okay, so that's my goal now. I'm going to say, okay, that's what I need to do. And since we know that that exists, what are we going to do? Well, this is how I'm going to set it up. I'm going to say, okay, let's just start with this. Take any x and the point that we care about. And let's look at this difference. This difference is equal to itself. Yeah? You buy that?
Yeah.
Buy that? Why would I do that? Well, because I'm trying to set something up. You know, because I know, since I know that this exists, I want to use it. And so what I'm going to do is say, okay, let's do this. X minus a right here, x minus a right there. Is that the same thing?
Yes.
Okay, so really, I'm starting with this, and I'm thinking, how can I do some stuff and blah, 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 mess around with it, okay, and so this is what I'm doing. Now, this is what I'm going to do. I'm going to say, well, hold up. So this is true. You're telling me that that's true?
Well, what if it?
Yeah.
When you there could be like a hole there after you add the.
Let me see. Hold up. So you're saying f of a equals There's what? Well, yeah, but what I'm about to do... Good point. There could be, like, what if x is equal to a? So I could say, let x not equal a. Now,
Yeah.
do you buy that?
Yeah.
Yeah, okay. But this is why I didn't bother to say it, because this is the next step I'm going to take. The limit as x goes to a. The limit
Or you can take
as
limit.
x goes to a.
Oh, yes.
Does everybody buy that?
Yeah.
So you bought that this was equal, and you buy that you could take the limit of both sides. If two things are equal, you could take their limits and they're still equal.
Yeah.
Yeah, okay, good. So we all buy that. So, by the limit laws, right, this is a product, right? And so the limit laws tell me I could take the limit as x goes to a of this stuff, f of x minus f of a over x minus a, and then just multiply that by the limit as x goes to a of x minus a. Yeah? Limit laws, okay? Because, and you're like, well, wait a minute, you could only do that if that's non-zero. But this limit exists, so it actually cancels out somewhere, doesn't it? Oh, cool. That's kind of cool, by the way. Like, you might have just missed that. I did. Like, I just thought about this just now. Like, whoa. For that to work, you have to make sure this doesn't blow up. If this blows up, all bets are off. But it doesn't blow up because we're assuming it exists. So it doesn't blow up. It's perfectly good.
Yeah.
Like, yes, it goes to zero, but we know that for it to exist, there must be some kind of cancellation that gets rid of it, and so we don't need to worry about it. Okay? Okay. So, what's this? What's the limit as x goes to a of x minus a?
Just x minus. Wait.
So here's the thing.
Negative a.
Is that thing a
Or
polynomial?
zero.
Is x minus some number a polynomial?
Yeah.
Yes.
So can I just plug it in?
Yeah.
Yes.
So
Okay.
it's zero.
Yes.
So this is the same thing as the limit as x goes to a of f of x minus f of a over x minus a. And this, we could see that, like, that limit is the same thing as a minus a, which is just a zero, so that's times zero.
The whole thing.
And so you take anything, it exists, so it's not infinity, and it's so we don't care, right? The only way you might have a problem is if you're multiplying infinity times zero. Sometimes it's zero, sometimes it's infinity, sometimes it's some other number, but we don't need to worry about that because it exists. By assumption, it exists. Since it exists, it's a finite number. Times zero is zero. Okay? And so, what did we just show? That this minus that is zero. Not quite done yet. We're not quite there, but we're so close. We're saying that you take this, f of x minus f of a, and you get zero. Okay? That's all I've shown thus far. Everybody believe that?
Yeah.
Everybody, okay, everybody follow that and we believe it. So that's the first, like, part of the result that I need. Now I need to show that the limit of f of x is equal to f of a. Well, let's see, what could I do? This is a nifty trick. If you ever take analysis, you'll be really used to using this trick. In fact, when you see this trick, you're gonna go, oh man, I've seen this somewhere before. So I'm gonna go ahead and do this right here. Boy, I wish I had an f of a in there. It'd be really nice if I could just magic up an f of a.
Add one and one.
Isn't that a great trick? Right? So it would be nice if I just had a minus f of a in there, but I can't just do it on its own, and so I'll just add it and subtract it.
Yeah, it's like the.
Oh
Difference
man.
of squares.
Is it
How nice
It's
is that?
complete-
Man, we don't have to do
completing-
difference to anything. And this is the thing. That's how we remember, that's how we did it,
Yeah.
right? Was when we're trying to complete the square.
Yeah.
And I said, add and subtract this thing. And no book teaches you to do it that way. But it's a really nifty trick when you're like, man, if I could just get a minus f of a in there. Just add it and subtract it. Now you got it. This is equal to that, yes?
Yeah.
Cool. So now it's a limit of a sum. So I could do this. The limit as x goes to a of this guy, f of x minus f of a, plus the limit of the second part as x goes to a of just f of a.
And that's zero.
This is zero because we just proved that it was. So that's zero plus the limit as x goes to a of, there's no x in there. This is just a constant. right? F of A,
Yeah.
there you have some function, you plug in your A, you get out an F of A, and it's like 5, right? Whatever it happens to be. It could be pi, it could be -7, doesn't matter. Once you plug it in, that's just a number. So X doesn't matter. This is just some number, and since it's a constant, that's what it is. And that's what we wanted to show. The limit as X goes to A of F of X equals F of A, and therefore it is continuous. Therefore, F is continuous. So again, if differentiable, then continuous, but the reverse does not work. If continuous, not necessarily differentiable. Now I'm going to blow your mind real quick. You might think, what kinds of functions would be continuous but not differentiable? And there's a lot of it. So there, it turns out, huh? We just saw one, but that was only at one point.
Yeah.
Right, you have, and so you can imagine, like, yeah, of course, like I could do something like this, and then there's a corner, and another corner, and so then, yeah, it won't be differentiable here, won't be differentiable here, I don't know what I'm drawing here. By the way, if your tangent line is vertical, you're not differentiable where it's vertical.
Oh,
Because your tangent line's vertical, like that would mean that you took the limit and you got infinity. That limit doesn't exist, so by definition, blah, 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 blah. But get this. There are functions which are continuous everywhere on all real numbers. They're continuous. Continuous, and so you think of continuous as being nice and smooth like this, but it turns out they're differentiable nowhere. And what these functions look like is if you zoom in on them, they're jagged. And then you go, oh, but this part right here looks smooth, and so you zoom in on it, and it's jagged. And you're like, oh, there's a smooth part right here, and you zoom in on it, and it's jagged. And so,
how does that work?
and so, later on this year, I might be able to tell you how. But that's not the mind-blowing part, by the way. So it turns out like that, you can have a function that's continuous everywhere. Everywhere it's connected, and the limit going anywhere goes to one place, but there's no derivative there because it's everywhere as a corner, kind of. Like you could think about that. Every single point is a corner, but it's completely continuous. Now here's the mind-blowing part, is that almost all continuous functions are like that. What does that mean? You take all the continuous functions and put them in a bag. Take every single continuous function
I guess that makes sense.
that exists in the world, and you put it in a bag, and you reach in, you're guaranteed 100% of the time to get one of these functions that's continuous everywhere but differentiable nowhere.
Well,
Yeah.
not every time.
Wait, so they're all jagged?
Yes, and this is the thing. You say there's no such thing as 100% of the time. In math, there is. Is that there are so many more of these functions than there are of smooth functions that the odds of you reaching in and grabbing one at random is 0.
Wait, so like sine is jagged?
No.
I guess yeah, if there's
No, it's just that the only ones that we're ever going to talk about are this tiny little class of of continuous functions that happen to be differentiable. Yeah, it's crazy stuff. So, okay. We got a few more things to get through. Oh, good. Not too bad on time. So, now here's one thing that we can say. So, we could say if differentiable, then continuous. Now, what does work in the opposite direction is if not continuous, then not differentiable.
Yeah.
And this is like, think about it. If Spot is a dog, well, no, that doesn't work. If Spot is a Dalmatian,
Not a
then
dog, he's not a dog.
Spot is a dog.
Yeah.
Now you can't say if Spot is a dog, then Spot is a Dalmatian. That doesn't work. But what does work is if not Spot dog, if Spot not dog,
Yeah. It's not. So you can switch them in and
Then-
both, yeah.
Spot
Like logic class.
not dog. That's exactly what this is. right? And so, since we have if differentiable then continuous, you could say if not continuous then not differentiable. And so, there you go. Okay, that will help you. So you're looking at a function, and it does something like this. And here's A, and they say, is f differentiable at A?
No.
No, because it's not continuous. You have to be continuous before you could be differentiable. It's not continuous there, so it's not differentiable there. We don't even need to think about it. Okay? Another way that you could be not continuous is if there's a corner. Something like that. That's actually called a cusp. I've never heard it called a corner before. Maybe a cusp is a special type of corner. I don't know. But like where it comes up to a point and then comes back down instead of something like a right angle or whatever, right? But who cares? It doesn't matter. That's not differentiable. And geometrically you could see because, well, you can't draw a tangent line there. All of these might work, right? So, but we know from the work that we just did, there's another way of doing that, blah, 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 blah. Okay, so that's how you could not be differentiable. Another way is if there is, I just said, a vertical tangent line or an asymptote. You're not differentiable there because, well, how could you be? Right? Not only are you not continuous there, like, I mean, come on.
You're not.
It ain't happening, right? Okay, so now check this out. We saw this guy last time. So here's f of x equals x squared. And we found last time that its derivative was what? F prime
It's 2x.
2x. Okay. 2x is just a line, right? And it just looks like this. Yeah. Okay, check this out. Geometrically, what's going on? And this is, you're going to do so much of this for the rest of your life, but pay attention, okay? I actually drew a point on my ruler. I've sullied my ruler for this, okay? We're imagining now that we're at some point over here, and we want the tangent line right there. So imagine, now what's the slope of this line right here? Is the slope positive or negative?
Negative.
It's negative, okay? Is the value of this positive or negative?
Negative.
No, it's a
Negative.
It's a negative value, right? So when we're here, let's say this is -2. We're here at -2. We could just plug it into this and see that that's -4. Let's say here's -1, and here's -1, and here you'd be at -2. Here's a 1. Here's a 1, you'd be at 2, and here's a 2. +2, you'd be up here at 4, right? 4, okay, so look at what's going on here. Over here, my slope looks negative. Over here, it's still negative, but it's less negative. See what's happening here?
Yeah.
When I'm at -2, my slope is steeper and it's negative. But as I move from here to here, it's still negative, but it's getting less negative, right? Here, you'd say that slope is like -2. And if I could draw perfectly, it would be like a -2, but whatever, right? You see what's happening. Keep moving your point along, and without looking down here at 0, what does that slope look like?
0.
What's the value of this function right there?
Also 0.
Also 0, okay? Now let's keep moving along, and my point gets to here at 1. And it looks like, well, it's a positive number, okay? And down here at 1, my value is a positive number, it's 2. And as I move over, the slope looks like it's getting steeper, right?
Mm-hmm. So 4.
And so a bigger number, like the slope, and if I did this perfectly, we could do like my rise and my run and say, maybe that looks like a 4. And you come down here and say, oh, the output value is a 4. And so that's what the derivative, you can think about it geometrically as just, again, a record of the slope, or a record of the speed, right?
So the slope is increasing constantly. Like
the slope is increasing at a constant rate. It starts off negative, and it's just constantly increasing, right? The slope itself is going from a negative number, it's negative, and it's getting bigger. Now it's 0, now it's positive, and it keeps getting bigger and bigger and bigger. Now, so does that make sense what I just did there? Okay? Is this a function?
Yeah.
It's a function. So we could take its derivative.
Yes.
Wait.
Right? It's just that, like, if I called this g of x, I could say, find g prime of x. Or I could say, you have a function, take its derivative. If that function happens to be a derivative, what you get is what we call the second derivative. So you have a function, you have its first derivative, and now you have its second derivative.
And then
you tell me, what? We're not going to plug this into anything.
It's just 2.
Well,
Because the slope is always...
The slope is always
Yeah.
2. And so if you're, again, like what we could have done is not done this. And I could have, if I could draw well, I could say, okay, what's its slope there? And we estimate, it looks like a -4, so I put a dot here. We move over a little, what's its slope? It's like -3, so I put a dot here. Then I move over here and say, the slope's about -2. Okay, I put a dot here, and I keep going. When I get to here, I say, okay, it's here, and so on and so forth until we get all of it. Here is really easy to do, because I can say, what's the slope here?
2.
What's the slope here?
2.
What's the slope here?
2.
So you're telling me it's 2 everywhere.
Yes.
The slope of this function is 2 everywhere, okay? And so its derivative should look like... So the battery died at the end of the lecture there. I'm just going to finish up what we were talking about, right? You have a function, you could take its derivative. But that derivative itself is a function. And so you could take the derivative of that. And like we did with this one, this is just a straight line. 2x is just a straight line. Its slope is always 2, no matter where you are, right? And so we deduced that the derivative of the derivative, the second derivative, okay, so you have a function, like we said before, this is like an operator. This says, take the derivative of this thing. And what you get is a new function. We call it f prime, or the derivative of f. We could take that. That thing itself is a function, so we could take the derivative of that, and what we get is a second derivative, f double prime, however you want to say that. And when we did that, we got, or we assume, deduce, that it should just be the constant function 2. Now let's do that analytically here, okay? So we have some function and we want to find its derivative. And so it should be the case that to take the derivative of the derivative, well, we're going to take the limit as h drops to 0 of that function, which is that function right there, f prime of x plus h minus f prime of x all over h. And so now we're just going to fill this stuff in. If I plug in an x plus h into that function, we're going to get, well, 2 times x plus h minus, this is just f of x, or f prime of x, which is just 2x, all over h. Now, okay, I have the problem with h, and so to get rid of it, hopefully something's going to cancel out. I'm just going to multiply everybody out on the top, and hopefully something will work. So that 2 goes into there, 2x, 2 goes into there, we get 2h minus 2x. Okay, the 2x's cancel, 2x minus the 2x cancels, and we get the limit as h goes to 0 of 2h over h. The h's cancel, and we get just the limit as h goes to 0 of 2. That's a constant, and so it should just be 2. So yes, indeed, right, the second derivative, it's f double prime right there, of x is equal to 2. And that's what we get. Now, this is a function, right? And so we could take the derivative of it and get the third derivative. Okay, so symbolically here, we have a function. It happens to be f double prime. It itself happens to be the second derivative of some original function. And we could take its derivative to get the third derivative, f triple prime. Yeah. And so, what's the slope of this thing? Well, it's 0, and it's always 0, right? No matter where you are, when you're here at x equals 0, the slope is 0. When you're here at 5, the slope is 0. When you're here, it's just always 0. So it should be the case that f triple prime of x is just, again, the constant function 0. Which is just, well, I guess it's just the x-axis right here, right? It's just that function right there. Same thing as that. It's just now it's just been shifted down 2, right? It goes through here at 0. Okay. And we could keep going, actually, because this is a perfectly good function. Its slope happens to be 0 everywhere as well. Maybe let's just see this, right? We have a second derivative, we're taking its derivative, which means that we're going to take the limit as h goes to 0 of f double prime of x plus h minus f double prime of x h, which is, well, I guess that's just 2, because it's always 2. Limit as h goes to 0. So this is just 2 minus, well, this is still just 2 because it's always 2 over h. So that's a big fat 0 over h. Limit as h goes to 0. And you might question about this. Be like, well, does that go to 1 or something like that? But think about it, right? This is just 0. So this is just the constant function 0. Doesn't matter what h is doing, right? As h goes to 0, that doesn't change what the numerator is doing. The numerator is already at 0. And in fact, if you were thinking about this, like that would just be very much like this. You just have, doesn't matter what h is doing, because h doesn't even show up in there. I mean, we could do this, it would be better to just show it rigorously, but since he's already at 0 and h isn't yet at 0, you take 0, divide by anything, it's still just 0. And so it's basically a constant, and it's just 0. Okay. And so you got that. The third derivative is itself a function. Again, it's a constant function, right? But that's a perfectly good function. So we could take its derivative. Right? We have the third derivative. 1, 2, 3 derivatives. We could take its derivative. Now, after this point, we are not going to go 4 primes. That's just, no, we don't do that. We're going to, once you get to 4, you start doing that right there. Okay? And so the fourth derivative of this function is just 0. It stays 0. And you could, it's still a perfectly good function, so you could keep going. You take the fifth derivative, and it's 0. And you could go on and on and on forever. And the nth derivative of this guy would indeed be 0. Now, you might assume that all functions, if you do take any function in the world and you keep taking its derivatives, eventually it'll get down to 0. That's not true. It is true for polynomials. Okay? All polynomials, you start with any polynomial and you keep taking derivatives, eventually you'll get down to 0. But not all functions work like that. And we're going to see some soon that do other things. So there's a couple more things I want to say. So in the same way that we have the, this is the prime notation that we've been using, you could also, so for instance, you have some function y, and that would be its first derivative. You could say that's the same thing as taking dx or t, depending what variable y is a function of, and say, okay, take the derivative of y, and you get y prime, the first derivative. So And we write that as dy dx. You could, again, like we're saying, take the next derivative of that thing, and this is what it looks like now. We don't write it like that, right? We're saying take the derivative of this thing, right? Which is the same thing as saying take the derivative of this thing, right? It means the same thing. Now we don't, but when we write this guy out, we have a nice nifty notation for that, and it's d squared y dx squared. Okay, and then you could take the derivative of that, and that, by the way, is the same thing as the second derivative of y, or f, you know, whatever the name of your function is. But this continues on, and you could take the derivative of d squared y dx squared, and can you guess how you'd write that in this? Yeah, it would be d cubed y dx cubed, and so on. And so you keep doing this, and so on and so forth, and you get the nth derivative of y dx to the n, which is the same thing as y with n little primes up there, right? And so d cubed y dx cubed is the same thing as y triple prime, and you keep going, and then you get this thing right here. Okay, so the last thing that we're going to do is actually talk about, we're going to get more into the geometry here. And this will be really, really useful. What we're about to do is a great exercise for you to get the feel for derivatives, like what a derivative is, how you could use it, etc., etc., etc. And there is an example in your book. I'm going to approximate that example. I think this is number 4. It gives you a function f. And it looks something like this. So here's your f. And it wants you to draw a graph of its derivative. Okay? And so we want to draw the graph of f prime. Now, one thing you're going to notice right away is there's no numbers here, right? We don't know if that's a 1 or a 500, right? So what we're looking for is a qualitatively accurate graph. We want it to basically do, well, later on we will be getting more into the particulars of this, and we'll want it to be more accurate. But for right now, we just want a general picture of what's going on. So I've done the function itself in blue. I'm going to do its derivative in green. And let's just think about it. So again, like we did with the parabola a second ago, you know, you could just go from left to right, put a dot up there and see, okay, what's it doing? And then from there, infer what the derivative should be at that point. That's what we're going to do here. But there's a special way I like to do this. Yes, in general, we are going to go from left to right. So remember, here's my point, right? And we're imagining this point here, there at 6, moving along the graph like this. So it starts like this, and it's going to come along and do this thing, and then do this thing, right? And that's what we're going to do. But there's a couple, actually here, there's 3 interesting points where we'll, again, like, since this is just drawn right here, if I start right here, I don't know whether that's actually like a -2, or is it supposed to be closer to a -10? You know, is it a -1? I'm not sure. I can tell that the slope is negative, but nah. But one thing I can tell you is right here at this point, what's its slope? Its slope should be 0. And so if the slope is 0 here, that means that the value of f prime, which is the slope, at whatever point this is, it should be 0 right here. This is where I like to start. I'm going to find all of my zeros first. In other words, I'm asking myself, where does the slope equal to 0? Well, not there, not there. Up, the slope is equal to 0 right there. So that means since the slope of f is 0 here at x equals 0, right? Since that's the case, then here at f prime equals 0, its slope should be 0, which means it goes through here. The value of its slope is 0. So the output value of this is equal to 0. And ditto again right here. Right, so I'm going to go just below it and say, okay, the slope of f is 0 here, and so the value of its derivative must be 0 there. Now, here's something you don't necessarily need to do it this way, but let's just think about the sign of the slope. Not S-I-N, S-I-G-N is the slope positive or negative in these various places. So, for instance, here the tangent line is going down, and so it's a negative slope. So it's negative, negative, negative. It stays negative, still negative, still negative, still negative, 0. And so I could say, at least in this part, right here, it should be a negative number. And then as we go from here, now it's positive, the slope is positive, it stays positive, it stays positive, it stays positive, it's positive, it's positive, it's 0. It was positive this whole time, right here. Okay? Now again, we could say, okay, what happens to this thing here? Well, it's 0, and so now it's negative. It stays negative, it stays negative, it stays negative, it's getting more negative. Oh, it's getting less negative, but it's still negative, less negative, less negative, less negative, less negative, and now it's 0. And so it was negative this whole time. Slope was negative. Now, finally, the slope is 0. Now the slope is positive, and it's getting more positive. It's positive, and it's increasing. The slope is getting bigger and bigger. And so it was positive the whole time. Okay. Now, for this part, what you could do is just think kind of like a parabola, right? If you remember back to Algebra 2, we did this. We don't know, we had a very similar kind of thing. You know that a polynomial, say, is negative here, it's 0 here, it's positive here, 0 here. Well, it must come up and come back down. And then if you remember, the question was, does it bounce back up or does it go through? And we could look at the sign and say, well, since it goes from positive to negative, it must come through. And you could do that same kind of thing, right, where you have these 3 dots. You know it goes negative, positive, and so you could just go, okay, negative, positive, it must look something like that. But I'm going to suggest that for this homework, and for the time being, that you think a bit more carefully about it right now. And shortly, we will actually get into some more finely grained things. But for right now, what I suggest you do is you grab a pen, grab a pencil or something as you're doing this, just like I'm about to do with this ruler. And it's too bad I am left-handed because this is going to make this hard. But I'll just do this right here, okay? And you just think, okay, it's negative there. And so this is where I'm going to start drawing. It's negative, and it's also quite negative, right? We could pretend it's like negative 10. And as it comes up, it gets less negative, less negative, less negative. So that means that the value is going from, say, like negative 10 up through like negative 5, up to negative 2, right? That's what's happening to the value of this slope until it gets to 0. I'm sorry, I was putting that here. I've meant like the actual value of it. And so this is what's happening. It's going from here coming up like this, okay? And so imagining it does something like this. Now, here, the slope is 0. That's why it goes through here. And as we go this way, it's starting to get more positive, starting to get more positive, starting to get more positive. It keeps getting more positive until it gets to a point where it kind of maxes out. It's not continuing to get more positive as we go up, right? It gets to a point where it stops getting positive, and then it starts getting more or less positive. It's still positive. It's still a positive slope. It's just coming back down. So it goes up, and then maybe about halfway through, it maxes out, and then it starts coming back down like that. And so I can imagine right about here is where it should get to its max, right? So something like that, right? And you can see what's happening, right? The slope is 0 here, and so the value of the derivative is 0. The output value of the derivative is 0. And so now the slope is getting bigger as we move, right? Slope is getting bigger, and then right about here, it's at its biggest. Now the slope starts to come down some, until finally the slope gets to 0 right there. And now you could use symmetry and say, well, this picture is the same, so it should just be kind of like some kind of mirror of it. But it's not. You can see it's not going to bounce back up and give you a mirror that way. It's rather that now, although I don't suggest that you do that. I suggest that you do it this way, like I'm telling you. Trace it along, right? Take your pen and put it up here, and now go, okay. It moves over and it starts to get more negative, so that means it should start coming down. The slope, as we go this way on F, the slope is getting more negative. So it should, the value of F prime should be coming down, should be getting more negative. And it does the same kind of thing where it comes down, it's getting more negative, more negative, more negative, more negative. Then it hits its most negative point. Now it's still negative, it's still a negative slope, but it's getting less negative. It's getting closer to 0 until it gets to here. And so what we should see is getting more negative, getting less negative, back to 0. So getting more negative, getting less negative, back to 0. Just so you know, these points right here, which correspond to the change, well, we'll get into what that's called. Those are called inflection points. And that is, like we said before, right? You have some trend. The slope's getting bigger, 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 up, slope's getting smaller, slope's getting smaller, right? And so we call it's an inflection point. It changes that, and it corresponds to either a max or a min down here in F prime, but we'll get to all that. So now we're here, and what happens? Well, the slope gets bigger, slope gets bigger, slope gets bigger, slope gets bigger, and it's a positive slope, so it's a positive. It starts at 0. It's a positive number that keeps getting bigger as we go to the right. And so I could say as we go to the right, it keeps just getting bigger. So it should look something like that. Sorry about that. That looks terrible. But that's the idea with this, right? And I said, and again, you could have just done one like I did. You say, okay, it's 0 there, so it'll be 0 here. The slope 0 there, it should be 0 here. And then say, that's some kind of polynomial looking thing, so it's going to be some kind of polynomial looking thing here. And then you just figure out, well, it's negative here. You could do that, but for right now, it will be really very much in your interest to do this whole tracing out thing that we're doing. Here's another example. It looks like I've kind of drawn it like number 10 from the book, but I've kind of done it a little bit differently too. So let's just, a quick once over before we actually get into it. I just want to see what's happening, right? So here's my tangent line here at the far left. Looks very negative, so it should start very negative and get less negative. And did I draw that flat? It's kind of hard to tell. And maybe you can't tell with the book. But let's go ahead and make it a little less ambiguous and say that yes, indeed, it does flatten out. Okay, so it comes down, it flattens out and then comes down. So we'll say it gets flat right there. Now, the book might be a little ambiguous or hard to see. Just use your best guess here. This is just that you're going through this is what matters, okay? So it starts off negative, but it's getting less negative, so it must be f prime starting negative, but increasing, right? So the slope is increasing, and then it looks like it gets to 0. Okay, and then it starts decreasing again. Okay, so it decreases. It doesn't look like it gets vertical. Maybe in the book you look at it and think, that looks like a vertical, a vertical tangent line. If that were the case, maybe we'll do one of those real quick and we'll see. Let's say that this goes vertical. We'll do that over here. I didn't draw that to be deliberately vertical, but let's say that this did get vertical right here and then comes back over like that. Just so I could show you how you would deal with something like that. But in this case, I'm not drawing it as vertical. It just gets quite negative. And then it's still negative, still negative, still negative, still negative. It's getting less negative, and it looks like right here we're at 0. Okay, so now we continue on. It's going to increase. Now it's positive. Okay, so it's positive, it's getting, it gets a little less positive. Okay, and now it gets more positive, more positive, more positive, more positive, more positive. Oh, vertical, yikes. Then it starts getting less positive as it moves this way. Okay, so back to now, so now that I have a general idea of what's happening with it, I'm going to say, okay, let's find the zeros. It looks like a 0 there and a 0 here, so I'm going to go ahead and do that. The slope is 0 here at that point, whatever x value that is, and then at whatever x value this is, it's 0 here. Now, let's think about this. Starts very negative and then abruptly gets less negative. So that means it must start very negative and quickly shoot up to get to 0. So I'm going to go ahead and do that. Something like that. Starts very negative and gets less negative and gets to 0. But now it doesn't go up through it, right? It comes back down. It gets negative again. So it very negative, 0, and then negative again. And so, since it's getting negative again, it must come back down that way, right? And so it's going to continue to get more negative and more negative and more negative until we get to about that point right there. So that must be where it comes down. That must be the lowest that it gets, because that's the steepest right there. But now it starts to get less steep. In other words, f prime starts to get bigger. It's getting bigger and bigger and bigger back up to 0. So that's where it got the most steep, and then it got bigger and bigger and bigger back up to 0. Okay. Now from here, again, you could just draw it, right? But I'm going to try to be a little bit more specific here, because it looks like it's 0. And now it's getting bigger and bigger and bigger and bigger. Oh, but now it starts to slow down a little bit. So it's increasing. The slope is increasing until it gets to here, and then it starts to decrease. The whole time it's still positive. So it should increase and then decrease a little, right? You see that? At 0, it increases and then starts to decrease right about here. So increases until it gets to here. And it decreases a little bit until it gets to here. Right, the slope itself comes up, the slope comes back down until it gets to about here. Now it takes off again. Now it looks like it's getting steeper the whole time. It's getting more and more positive until we get to that point, and so it's increasing, increasing, increasing. Now, if that's 0, and that's 1, and that's 2, and that's 10, and that's 1,000, that's 1,000,000, that's 100 million. When you're exactly vertical, then it must shoot off to infinity. So here at this point, we must have an asymptote. But then we start coming back down to reality, right? It comes off from, it's still positive, right? It's not a negative. It doesn't automatically give you a negative. It went from infinity to less than infinity. And as we move this way, it's coming back down to reality. So what it should look like is just after here, it went from infinity to come back down. Something like that. That's what f prime should look like. The derivative of f. We're just keeping a record of the slope of f the whole time. There's one more thing we need to talk about. And this is just as an aside, really. But the more that you do these, like, it's a really good exercise to actually go through it the way that I did and reason, like, kind of point by point as you go through and say, it's getting bigger, it's getting smaller, the slope is doing this, which means that the derivative does this. That'll build your intuition for derivatives and functions. So it's a really good thing to do. So, yeah. We'll do one more. Actually, I was gonna stop it there, but I do want to do one more. Let's do. 'Cause I know that one's in your book. I don't want to give you the one that's in your book, so here's your function. And it looks like a half circle, so maybe it is a half circle, but whatever. There's your function f. Perfectly good function. Okay, it may not be defined everywhere, but it's a good function. So let's see what happens here. So now we want to draw f prime. And so we're going to go through, start on the left-hand side. I can see it's negative. In fact, the way that this looks, assuming it's a circle, the way that it's drawn, if it were a circle, you could imagine that this, the rest of it were there. Its tangent line at this point would be due vertical. And thinking about it, it's not this way vertical, it's vertical down, so that should be negative infinity right there. But as we move, it gets bigger, right? Or it goes from negative infinity and increases, or you could say that the slope itself, the magnitude of the slope gets smaller until it gets to 0. And then it goes up and gets positive, and then shoots up to infinity again. And so here, another thing, I didn't say this a minute ago, but a good thing, like I said, I always like to, and I'm going to pretend I drew this perfectly so that the 0, or when the slope of f is 0, I'm going to pretend is right here, and so I know it goes through 0. And I said the first thing I want to do is go through, find all the zeros and do that. You should also find asymptotes too. I know we have to have a vertical asymptote here because they have a vertical tangent line, and so do that. Same thing over here. Somebody goes off to either plus or minus infinity. And so must start at negative infinity and make its way up. And it looks like it's slowing down too, right? We go from negative infinity and shoots way up to like negative 10 just over that much distance. So it must be coming up really fast and then slowing down, right? Something like that. I could be wrong. I don't know. Then let's see. Now it's slowly working its way up, Now it took about that long for it to get to the value 1. And now it took a little less to get to the value 2. And now it's it's already up here at 10, and we can see it shoots off to infinity. So maybe it does something like this. Now at this point in our study, we don't know whether or not it did something like this, or if maybe it actually went down like this. Maybe it shot up quicker, but I could kind of see that it's not, like by the same reason I was saying. It takes a while for it to increase to about 1, right? So here it's at 0, and it took a while for it to get bigger. Now here it's about at 1. Now not as long to get to 2. Now, whoa, not long at all to get to 10. And then if I move a little bit, now I'm getting a huge thing. So I guess at this point you can reason that it doesn't shoot way up first and then move over. It should take a while for it to shoot up. But there's a much easier way to figure out the shape of these, which we will go into later. It's not necessarily easier. In fact, this is about as easy as it gets. But to confirm that that's indeed the case, we'll get into that stuff before too long, really. Now, there's only one thing left I wanted to say. And that was the very first day we talked about a function where the input was time in, I think we had hours, and the output was distance in miles. And we said you have some kind of record of your travels, right? In other words, you have a graph of your position versus time, or distance versus time. And let's call that guy f. We'll say it's f of t. And so f of t, we could say it's not equals, but it corresponds to your position. Right. So if you have a graph that's position as a function of time, then its derivative, we said, right, f prime of t, which is its slope at any point, right, our change in y over our change in x, delta y over delta x, would be your f prime. Its units would be in miles per hour. And so this is just review. We've already talked about this. This would be your speed, right? Although it's not technically speed, it's called velocity. Why velocity? Well, because velocity can be negative, but speed is always a positive quantity. So for instance, if this was a record of where you were, this would mean that you drove north, you slowed down, you went faster and you drove north, then you stopped because your slope was 0. And you must have turned around and started driving south, okay? And so on your speedometer, it would say you're going, say, 60 miles per hour. But the slope here would be a negative number, right? Your rise over your run would be negative. And so velocity can be positive and negative, and velocity tells you which direction you're going. Speed doesn't tell you anything about direction. If during this leg of my journey I told you I'm going 60 miles per hour, you could say, were you going north or south? Velocity, if I tell you I was going negative 60 miles per hour, you'd say, oh, so you were going south. So that's the difference between velocity and speed. And indeed, a first derivative does give you velocity. And velocity is a change in position. Remember what I said about the derivative is that, like, this whole thing that we're setting up, right, it's a rate of change. How fast is your function changing? Well, since this function gave you position, the first derivative is its change in position. And what would its second derivative be? In other words, the derivative of the velocity, well, if this derivative is a change in the previous function, this derivative must be a change in that previous function, so it would be a change in velocity. What's a change in velocity? We call that acceleration. Can we take another derivative? Of course we can, right? That's a function. Well, if the function's differentiable. But if your original function was position, I could pretty much guarantee you that it will be differentiable. But anyway, the third derivative then. So if this derivative was a change in the original function, right? It's just a record of how does that original function change. The second derivative is a change in the previous function, then this must just be a change in the acceleration. And a change in the acceleration is actually a name for it. It's called jerk. You could think about that, right? Like if you accelerate, you hit the accelerator. As you're accelerating, you feel it. Then all of a sudden, if you hit the brakes, now you've changed the acceleration, you're going to feel a jerk, right? And that's why it's called jerk. So this is just stuff to know. It's probably going to come up a bunch. Like you'll certainly have a word problem saying like, you know, given such and such position, blah, 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 find the acceleration. You'll need to know that, oh, the original function that was given was a position, and I'm looking for acceleration, so I want to take two derivatives to get to the, so just like we did earlier, if I said a particle is moving and its position is given, position after time equals 0 is given by t squared, like it's heading due north or whatever, and I want to know what's its acceleration, you'd say, okay, well, first derivative, like we said, would be 2t. Second derivative would just be 2. And so it would be 2 whatevers. And here's the, might as well go into this, right? If this is miles and your time is in hours, then your velocity is in miles per hour. So then the velocity function here, I'll sketch this real quick. Let's do it. Let's see what it would look like with this being my f. Looks like it's very, very steep and slows down, so it comes up from high and goes to 0, so it does something like this. And it comes back up and back down. Now it's negative, and so it goes negative, back up, looks like to 0, then goes negative again, something like this. Okay, so now this f prime is in units of miles per hour, right? It's your record of speed. So on this axis we have miles per hour, and here we still have hours, and so its derivative would be delta y over delta x would be miles per hour over hours, so it would be miles per hour squared. Usually when we're going to be doing stuff, it'll be in meters and seconds, and so if your original graph were in meters and your time were in seconds, the first derivative would be in meters per second, but then the change in that would be meters per second, right? As you, right, the rise would be in this is miles per hour, this would be meters per second. The rise would be meters per second, and then your run would be in seconds, so it would be meters per second, or meters per second squared. That's units of acceleration, and so on and so forth. And so, if my original were miles per hour, then I would say that the units on this would be miles per hours squared, or if it were in meters per second, it would be 2 meters per second squared, and so on and so forth. When that stuff comes up in the future, we'll do a brief review of that, but it's just good stuff to know. So anyway, sorry the stuff or the camera ran out of juice. Try to not have that happen again. Take care.